Welcome, my dear learners, for this course on design of machine elements 1. In this module 1, we were discussing on design for static strength. In this final lecture on design for static strength, let us solve a special case problem, that is problem number 10, which has horizontal and vertical component of load, which is inducing different type of stresses in this specimen. Let us analyze problem number 10 in today's lecture and conclude our discussion on design for static strength. Moving ahead, the problem number 10 states that find the numerically maximum normal stress and the maximum shear stress at section XX in the member loaded as shown in figure 10. So this is the figure 10 given for us. So if you carefully observe figure 10, we have horizontal load acting on it, which is given as 500 Newton, and vertical load whose magnitude is 1 kilonewton. Let us analyze this load individually. If you carefully observe, he has given the side view of this here. In the side view you are observing 500 Newton. So therefore, which means that 500 Newton is acting from inside the board towards the observer, towards you people. It is acting from inside the board towards you people, which can be seen only in the side view. So therefore, in the side view he has represented it as 500 Newton. Whereas this can be seen in both the views. In front view also it is 1000 Newton, in the side view also we can observe it. Whereas this 500 Newton is not visible in the front view because this 500 Newton is acting from inside the board towards the observer. So like this it is acting. So therefore, it is visible only in the side view, which is shown here. Now we should analyze individually what is the effect of vertical component, that is 1 kilonewton, and what is the effect of horizontal load 500 Newton. And later on we can find what is the maximum stress that is induced in this specimen. Let us analyze one by one. First, let me consider vertical load of 1 kilonewton. If I move for solution of problem number 10, let us consider vertical load considering vertical load of 1000 Newton. So if I consider vertical load of 1000 Newton, the section XX is here. We have the section XX. So for this section, if I analyze, 1000 Newton is acting here and the section is here, you can see clearly it is an eccentrically loading. It is an eccentrically loading to the specimen here, which is somewhat similar to the problem which we have solved in our previous lecture, problem number 8 and 9, where we solved problems on clamp. Similar to that, we have load, the line of action of force 1 kilonewton is passing here, where the specimen is here. We have an eccentricity of 100 millimeters. So since it is evident that the section XX is eccentrically loaded with 1 kilonewton, it induces both compressive stress and bending stress. This bending stress is also compressive in inner fiber. So direct stress is also compressing. The bending stress is also compressing it in the inner fiber, whereas it is tensile in outer fiber. Since the direct stress is also compression and the bending stress is also compression in the inner fiber, the maximum, numerically maximum magnitude will be compressive stress in the inner fiber. So therefore, the vertical load of 1 kilonewton is causing eccentric loading. So therefore, the sigma direct from vertical load will be, load is 1000 Newton or 1 kilonewton, and area of circular cross section is pi d square by 4. Pi d square by 4. So therefore, this yields as the value as 1000 into 4. So this is nothing but load by area. So hence direct stress will be pi times 25 square, which is equal to 2.0372 megapascals, which is compressive. So therefore I should take it as sigma d. Let me write it like this. Later on when I find the maximum stress, let me take it as negative. So its effect is compression for inner fiber. I am analyzing only for inner fiber because bending stress is also compressive for inner fiber. Next we have bending stress, sigma bending, which is given by mb by z, where the value of z is given by 32 m pi d cube by 32, pi d cube by 32. So therefore this, if you have forgotten, you can refer table 1.3a, page number 12 of our data handbook. So bending stress will be equal to mb. How much is the bending moment? Load is 1 kilonewton, distance is 100. So therefore mb will be 1000 into 100. Eccentricity is 100, you can see here. Eccentricity is 100 divided by pi times diameter is 25 into 32. So therefore sigma b will become 1000 into 100 into 32 divided by pi times 25 cube, which is equal to 65.1899 megapascals. So this is the effect of vertical load. Vertical load is causing direct compression and bending compression. So this is also compression in nature, compressive for inner fiber, Next, if I take the effect of horizontal load, considering horizontal load of 500 Newton. If I consider horizontal load of 500 Newton, what is its effect? So horizontal load of 500 Newton is acting from inside the board towards to the observer on this member. So it will cause twisting like this. So this member is fixed here. It will cause twisting like this, and also it is causing bending like this. This member is bending and it is twisting. So it is the 500 Newton is causing twisting and bending like this. So therefore the effect of 500 Newton is both twisting moment as well as bending. Hence the considering horizontal load of 500 Newton, we have twisting and bending. So therefore how much is the torque? Torque T. For torque T twisting, we have 500 Newton and it is causing twisting. So therefore this distance is 100. How much is the torque acting like this? Torque is acting like this. 500 Newton is coming from inside the board towards the observer. So therefore it is causing like this. So 500 Newton into distance is causing the torque like this. So this distance is known, which is 100. So torque will be 500 Newton into 100 mm, which is equal to 5 into 10 to the power of 4 Newton millimeters, and it is causing bending MB. So at this section XX it is causing bending. So here is the load 500 Newton and the distance for bending is 125. So 500 Newton and bending. So it is causing bending like this. So therefore this distance is 125. It is causing bending. It is 500 cross 125, which is equal to 62500 Newton mm. Now how much is the bending stress from horizontal component? This is from vertical. This is also from vertical. Now torque will cause torsional shear stress. So therefore tau from vertical component will be 16T by pi d cube, which is equal to 16 into 5 into 10 to the power of 4 by pi times diameter is 25 cube. Hence the shear stress because of vertical component of load is 16 into 5 into 10 to the power of 4 divided by pi into 25 cube, 16T by pi d cube, which is equal to 16.297 megapascals. Now coming for MB, we have bending stress, so therefore sigma bending due to horizontal component is equal to MB by Z. For circular cross section it is given by 32 MB by pi d cube. So therefore it is 32 times MB is 62500 divided by pi times D is 25 cube. So therefore bending stress due to horizontal load will be 32 into 62500 divided by pi times 25 cube, which is equal to 40.744 megapascals. Now if you carefully observe, we have direct compression stress, bending stress due to vertical load, bending stress due to horizontal load, and torsional shear stress. So we have direct stress, we have bending stress, we have torsional stress, again we have bending stress which is compressive for inner fiber. I am solving only for inner fiber because both direct and bending stress are compressive at inner fiber. So now if you carefully observe, bending stress is there by vertical component and also by horizontal component. So therefore for bending stress let us take resultant. So hence now let us take resultant bending stress. This is because we have bending stress in both vertical component as well as in horizontal component. So therefore I should take the resultant bending stress will be sigma bending is equal to root of horizontal stress square plus vertical component stress square. So if I substitute and solve, I will get the answer as 65.1899 square plus 40.744 square under the root. So I will get the answer as root of 65.1899 square plus 40.744 square, which is equal to 76.875 megapascal, which is compressive in inner fiber. So now if you carefully observe, we have direct stress, we have bending stress, and we have torsion. You know how to solve when you have direct, bending and torsion. When all the three are there, we know how to solve. We should use maximum principal stress theory, minimum principal stress theory and maximum shear stress theory to solve such problems which has all the three loading cases, that is direct compression, bending and torsion. Now we know the value of direct stress having both compression and bending, sigma is equal to minus sigma d minus sigma b. Why I am using minus? Because both are compressive. Direct stress is also compressive, bending stress is also compressive, so therefore I am using negative sign here. Hence the value of sigma will be minus direct minus 2.0372 minus bending 76.875. So sigma is minus 2.0372 minus 76.875, which is equal to minus 78.9122 megapascals, which is negative because of compression. Now he is asking to find numerically maximum normal stress. Numerically maximum normal stress, since the sigma value is negative, I should use minimum normal stress theory, that is sigma minimum will become maximum for us. Sigma minimum is equal to sigma by 2 minus root of sigma by 2 whole square plus tau square. So this will gives us the maximum value. If I use plus, since here I have minus, that will gives us the minimum. So for compressive stresses, minimum principal stress theory will gives us maximum, maximum principal stress theory will gives us minimum value. So hence if I use this, I will get the numerically maximum normal stress. So if I substitute and solve, I will get the answer as minus 78.922 by 2 minus root of minus 78.9 by 2 whole square plus 16.2 square. So hence I will get sigma minimum, which is numerically maximum for us, that is minus 78.922 by 2 minus root of minus 78.922 by 2 whole square plus tau square is 16.297 square, which is turning out to be minus 82.155 megapascals, or numerically maximum normal stress, that is sigma max will be 82.155 megapascals, which is compressive in nature, Now if I go for tau max is equal to root of sigma by 2 whole square plus tau square. Maximum shear stress will be term under the root. So let me delete the first part and find out how much is the answer. Maximum shear stress is turning out to be 42.693 megapascals. So this is the complete solution for problem number 10, which is a bit tricky, wherein which we have compressive stress as the maximum value. At the inner fiber we have both direct stress as well as bending stress as compression, whereas at outer fiber we have direct stress as compression whereas bending stress as tension. So therefore that will give us the minimum stress. So for maximum stress we should go for compression. When we have compressive stresses as the maximum value, we should use minimum principal stress theory to get the numerically maximum normal stress. numerically maximum normal stress. So numerically maximum normal stress is 82.155 megapascal, which is compressive in nature, whereas maximum shear stress is 42.693 megapascals. So this completes our discussion on design for static strength. From next lecture, I will start a new topic, that is stress concentration and problems on stress concentration. That's all from this lecture. Thank you all.